when I was just starting my work in Bordeaux, Jean-Marc Desuyer introduced to me some Indian guest, kind of very like simple guy who just told me, call me Balu. Okay, Balu, Balu. And it took me some time to figure out that, well, this unassuming guy who wants to call him Balu, and the celebrated mathematician Bala Subramanian is the same person. So, and well, since then enjoyed many meetings, mainly in Chennai, but also elsewhere. And well, I'm happy to be here to speak on conference dedicated to him. Okay, so what this? It doesn't. Oh. Somehow. I don't know why. Yeah. Okay, I see. Okay. So the screen is perhaps a bit too big, at least in my because of the bar, I don't see the title of the page, which is a bit unfortunate. Maybe. Okay. So let me start. So in this talk, I will assume that, well, all algebraic numbers are just complex numbers. So by Q bar, I simply denote the algebraic closure of Q in C. And well, if we have an algebraic, non-zero algebraic integer of degree D, so alpha will always, unless otherwise specified, stay for a non-zero algebraic integer of degree D. And well, if alpha 1, alpha D are its conjugates, then we define the two famous functions, the Mahler measure of alpha, which is just product of absolute values of all conjugates, which are bigger than 1. And the house is just maximum of absolute value of the conjugates. And we have very clearly, we have the relation that both are greater or equal than 1, and of course house is smaller, less or equal than the Mahler measure, but the Mahler measure is clearly less or equal than the house raised to the power D. And well, classical 19th century theorems of Kronecker say that when alpha is root of unity, it's equivalent to saying that both house and Mahler measure are 1. And when alpha is not a root of unity, then house and Mahler measure are not just bigger than 1, they're separated from 1 by some quantity which depends only on the degree. Or I prefer to speak in logarithmic terms, the logarithm of the house is separated from 0 by some positive number depending only on the degree. And well, it was a question that interested many people since for more than 100 years. What is this constant? What one can say about this constant, C of D? And there are two basic conjectures about this C of D. One due to Derek Lehmer, yes, in his article in 1933, so like 90 years ago. He made the following observation, that Mahler's measure are not just separated by something from 1 by something from the degree, depending on the degree, but just separated by some absolute constant. At least he made some, at that time, he made some rather extensive calculations, which was quite heroic mission by that time. And he asked the following question. So I think it was not a conjecture, it was rather a question, a problem of Lehmer. Does it exist a positive absolute constant such that logarithm of Mahler measure of any algebraic non-zero algebraic integer, which is not a root of unity, is greater or equal than this constant. Like 30 years after, Schinzel and Zassenhaus published a joint article where they discussed this conjecture and made a slightly less ambitious conjecture that the house is separated by some from zero log of the house separated from zero by the expression of the form C over D, where C is some absolute constant. Well, clearly, since clearly that Lehmer's conjecture is a stronger conjecture, formally stronger. So if we prove Lehmer, we also prove the Schinzel-Zassenhaus conjecture, or not other way around. And well, since I think this work of Schinzel-Zassenhaus was the first work, non-conjectural result about, in this direction, and then followed many other works, but let me first discuss some trivialities so that we just don't stick into some trivial results. First of all, we cannot conjecture anything better than what we say, because, for instance, if we take as alpha the dth root of 2, then it's Mahler's measure, and also d multiplied by its house is log 2. So in both conjectures of in both these conjectures, both this C and this C, both these quantities C cannot be taken smaller than cannot be taken bigger than logarithm 2. Well, it's quite naive, but also, if alpha is not a unit, algebraic integer, but not a unit, then trivially both conjectures do hold true, and again with a constant log 2, because just it's all estimated from below by the norm of alpha, which is at least 2 in this case. So log norm is at least log 2. So indeed, the problems are interested only for units. And more or less implicitly, I will think of alpha as a unit, but I don't think that we will ever use in the arguments below that alpha is a unit. Actually, Lehmer made a more precise, again, let's put a question, that very probably he thought that the smallest Mahler measure is attained for the root of this wonderful polynomial of degree 10 that he discovered. And so far, I think now with our powerful computers, no polynomial is discovered whose Mahler's measure is smaller than this one. So probably he was right, Lehmer. And David Boyd again made some extensive calculations, and he conjectured that very probably the smallest value for degree multiplied by the log of the house is this quantity, 3/2 of log of theta, where theta is the real root of this cubic polynomial, and which is known as the smallest Piso-Vigevareх, or I can pronounce it, sorry, Piso number. Now, which kind of results we already have? Well, Lehmer's conjecture is still open, and there are many partial results. So I give here some list of some contributors, which is certainly not complete. There were more contributors to this problem. I believe two most important results about Lehmer's conjecture still date back to 70th. Chris Smith proved that if alpha is not a reciprocal number, and reciprocal means that alpha and 1 over alpha are conjugate over Q. So he proved that if alpha is not reciprocal, then its Mahler measure is at least theta, where theta is what already occurred in the previous slide, is the real root of this polynomial. And clearly for non-reciprocal numbers, so this establishes Mahler conjecture, Lehmer conjecture for non-reciprocal numbers, and the result is clearly best possible because we can take not only just this theta, but we can take all roots of this theta, and we again obtain for them the same Mahler measure. So one cannot say anything better for non-reciprocal numbers. And if we drop this additional assumption that the number is non-reciprocal, then the best known bound is a very famous result by Dobrowolski, who proved that, logarithmic Mahler measure is bounded from below by some, this strange quantity. Well, I like this article very much. I think it was the first mathematical article I ever read in my life, the article of Dobrowolski. And at that time it was kind of, when it just appeared, it was kind of thought that, it will be soon refined and so on, but it is not refined until now, only on the level of constant that I put here, implied constant. It is, it's refined by the asymptotics is still here. Well, there were many generalizations of this Dobrowolski Lava bound to more complicated cases like multiplicative groups of higher dimension, elliptic curves, abelian varieties, but the original result of Dobrowolski still stands as it is, so it could not be refined. On the contrary, the problem of Schinzel-Zassenhaus, which is, as we saw, is a slightly weaker statement, is now a theorem. On December 28 of 19, Veselin Dimitrov posted an archive his beautiful article where he proved that the log of the size of the house is at least constant over D. With a constant, he obtained this number. It's certainly not best possible constant, but at least it proves the conjecture. And what I will say in the remaining part of the talk. So first, I will revise Dobrowolski's argument. I will not prove this estimate, but I will prove some weak estimate. But I will show how it works. I think it is still very useful to know how Dobrowolski's argument worked, because it was reused many times, similar kind of ideas. Next, I will speak about some technical stuff needed for Dimitrov's work, which is quite beautiful. The old notion of transfinite diameter and the result of Dubinin on transfinite diameter of certain special sets. I will also speak on power series with integral coefficients and the classical theorem of Polya about them. And then I will try to present Dimitrov's argument. Hope I will have time for this. Okay, so far, I think before I start being more technical, any questions? Okay, then let me continue. Okay, so I will now speak a bit on Dobrowolski's argument. Dobrowolski actually published two articles. One in some obscure Polish journal where he gave the preliminary version, and I will speak on this preliminary version. And then the full version of his argument, this result with logarithms, he proved in the celebrated article in Acta Arithmetica. Okay, so now some preliminaries. So let f of t be just some polynomial. I don't say that just some polynomial with integral coefficients. I don't say that this is alpha that interests us, just some polynomial. And for this polynomial, we define fn of t, well, n is a positive integer, as the polynomial which has the roots, same roots as f, but raised to power n. So, and well, if p is a prime number, then I think it was a famous result which was discovered and rediscovered many times, kind of Schoenemann's congruence, that f and fp are congruent mod p, which means that their respective coefficients are congruent mod p. And more generally, I believe this was not present in the article of Schoenemann. Yesterday I looked through the two articles of Schoenemann related, but I did not find, perhaps I was not very careful. But it is not hard to generalize that if we take fpk minus 1 and fpk, then they're congruent mod pk. Well, it's a kind of famous phenomenon that Frobenius is a contracting map. So, well, if we have two guys which are periodically close, then their Frobenius are even closer. Well, as I say, it was discovered and rediscovered many times, and well, some among the rediscoverers were some big names like Deligny or Arnold or whatever. Well, anyway, and these two congruences are basic tools for both for Dobrowolski and for Dimitrov. And Dobrowolski uses just the first level, f congruent to fp, and Dimitrov uses the second level, fp is congruent to fp square mod p square. Okay. Now, what follows from this, that f is congruent to fp? It follows clearly that the resultant of polynomials f and fp is divisible by p to the power d. Because what is the resultant? We just take values of f at all roots of fp, and they're all divisible by p, so their product is divisible by p to the d. And if we take now product of these two polynomials, f and fp, and consider the discriminant of this product, what is the discriminant? It's discriminant of f times the discriminant of fp and times the square of the resultant. And so we obtain that the discriminant is divisible by p raised to the power 2d. And well, now we'll apply it in our situation. Well, alpha is algebraic integer of degree d, not root of unity. I always forget to say that it's non-zero. Well, assume that. And alpha 1, alpha d is conjugates, and well, f is the minimal polynomial, and we select p in the way so that the 2d numbers, all the conjugates of alpha and all the conjugates of alpha to the p are all distinct. And while it is, well, there is some easy lemma showing that it's not hard to find p like this. Actually, this is true for all p's with some very, very few exceptions. And so, since it is distinct, then discriminant is a non-zero number, and it follows that its absolute value is at least p raised to the power 2d. So this gives a lower bound for discriminant. So it is typical Diophantine argument. We obtain a lower bound using arithmetic. Now we will obtain an upper bound using kind of, well, analysis and calculation. And it's also easy to get an upper bound because what is discriminant? It's square of Vandermonde made of the roots, right? And so here is this Vandermonde, and well, it's very easy to estimate it using, for instance, Hadamard's inequality. Well, we apply Hadamard's inequality to the lines, not to the columns. And if we apply it to the lines, then the norm of the first lines give something which contributes. The first D lines contribute to the Mahler measure, and these lines contribute to the Mahler measure to the power p. And so we obtain at the end this kind of estimate, very simple estimate. So what we have upper estimate, and we have a lower estimate for the Mahler measure, and we compare for the discriminant, sorry, and we compare them, and this gives us a lower estimate for the Mahler measure. So p divided by 2d raised to some power, well, essentially 2 over p, yeah. And now we take, if we take p of order of magnitude like 4d, then this gives lower bound for the Mahler measure. The log of Mahler measure is at least some constant times log d over d. And then for the house, it will be log d over d squared. Well, these are not optimal results, but they are better than anything that was known at that time. So it was already a breakthrough at that time. But here we just used 1p. And Dobrowolski refined this argument. He took many primes p. And it's how he obtained his famous lower bound for the Mahler measure and, well, for the house. I don't go into this more technical argument, but I think this simple argument shows already the idea that was introduced by Dobrowolski. Well, the drawback is that, well, because we use Hadamard, we have this extra term 2D, and well, this means that we cannot take two small primes. If there were no 2D, then we're done with Mahler's conjecture. We just take p equal to like 3 or 5, and we're done. But unfortunately, because of 2D, we must take rather big p, and this results to these bit weak estimates. Well, I don't know why I put log. Maybe there is no log here. Maybe there is no log. It's just, yeah, there is no log. So I think I should erase it. But still, it was better than anything was known before. Okay. So now let us speak on the work of Dimitrov, but before I can speak on the argument of Dimitrov, I need to introduce some notions. First notion is the very classical important notion, which is almost 100 years old, the transfinite diameter of a compact on a complex plane. And what is transfinite diameter? Well, there are many definitions. Probably the easiest is the following. You take endpoints in our compact. You take the distinct points, or actually endpoints in our compact. We take the Vandermonde and normalize it. Just it is n times n minus 1 over 2 factors. So you just take this root, so kind of geometric mean of these factors in the Vandermonde, and take the maximum of all of these quantities where z1, z10 run of the points, and we obtain kind of delta n. And this delta n is a decreasing sequence, so it has a limit, and the limit is called the transfinite diameter. Well, there are many other definitions, like using conformal maps or capacity or whatever, but well, I think this definition would be enough for us. And well, there are some properties. The first two properties are totally trivial, like monotonicity. So smaller transfinite diameter of smaller set is smaller than transfinite diameter of the bigger set. Or it is, well, if you do the translation, you don't change clearly. If you do homotity, you multiply so it is homogeneous of degree 1, so multiplied by absolute value of the coefficient of this homotity. And well, it's slightly less obvious. Well, one needs some work to show that if you have a monic polynomial of degree n, and you take the inverse image of our compact, then the transfinite diameter of inverse image will be nth root of the initial transfinite diameter. And also for two important sets, for the unit disk, the transfinite diameter is well known to be 1. And also for interval -2, 2, it is 1. So for interval 0, 1, it must be 1/4. And this is crucial. That, well, not the exact value 1/4. It's crucial that it is smaller than 1. Okay, so this is all about what we need to know about transfinite diameter in general. Now let us consider some specific sets. We call a hedgehog a set like this. Just take some point on the complex plane and put several straight line segments out this point, and this will be called a hedgehog. And in particular, if we take, well, as initial point, we take 0, and the other ends, we take nth roots of unity, well, which form the vertices of regular n-gon, then we'll call it regular hedgehog and denote it Hn, something like this. And well, it's very easy to find the transfinite diameter of that regular hedgehog because it is the inverse image of the interval 0, 1 under this simple polynomial, just that to the n, and by the previous property, its transfinite diameter must be nth root of this, so nth root of 1/4, so 4 to the -1/n. Again, it's important that it's smaller than 1, and well, by some quantity which is of order of magnitude 1/n. And now comes the work of Russian mathematician Dubinin, also quite long ago. You see, all mathematics needed for Dimitrov's proofs was known for almost like 40 years. So we only wonder why it was not done before, because it's all the things he uses are very classical. And he considered the following situation. He considered hedgehog where still the vertices lie on the unit circle, but not a regular one, just arbitrary one. And he proved that its transfinite diameter is always less or equal than the transfinite diameter of the regular hedgehog.
Sorry for interrupting. There is a question. There is a question by Professor Desue. How is it that delta -1 to 1 equals to 1 and delta 0 to 1 equals to 1/4 and not half?
Sorry?
So, so there is a question on the chat which says that how is it that delta of the interval -1 to 1 is 1, but delta 0 to 1 is 1/4 and not half?
-2 to 2. It is of interval -2 to 2 is 1.
I see. Okay, thanks.
It's not -1 to 1. No. It's -2 to 2 because yeah, you take you take not the cosines for the roots of the Chebyshev polynomial, but twice the cosines. So it's like this.
I see. Thank you. Thank you.
Okay. And well, this of course clearly best possible result for this kind of configuration. And the consequence, if we just take totally arbitrary A1, AN, then the transfinite diameter of the corresponding hedgehog is again multiplied by this quantity, nth root of my 1/4, times the maximal of the absolute values. And this result is probably not best possible. And this is exactly the reason why Dimitrov can prove Schinzel-Zassenhaus, but cannot prove Lehmer. Because if here, instead of maximum, we're kind of a smoother function, or like, well, I don't know, geometric mean or whatever, then it would probably imply Lehmer. But, well, we have here only the maximum, and this is what we have. So, okay, another topic also related to the notion of transfinite diameter is a very classical work by George Polya, again in Hungarian stuff. And well, he proved the following beautiful theorem. Let K be a compact, and we assume that its transfinite diameter is strictly smaller than 1. And we assume that if we the complement of this compact in the extended complex plane, so supplied with infinity, is a simply connected set. I believe that this assumption is not needed, but well, things become a bit delicate, so I prefer to impose it, so not to think about some technicalities. Well, and now let U be a function which is a regular function on this complement, and which has the following property, that its Taylor expansion at infinity has coefficients, has integral coefficients. Then it is a rational function. So crucial here is, of course, the assumption that the set that we throw away is small, has small transfinite diameter. Already, if we just throw away, for instance, the unit disk, we can find plenty of series which have this unit circle as natural boundary, plenty of series with integral coefficients. So it is indeed, it's indeed the crucial assumption that the transfinite diameter is smaller than 1. Well, initially I planned to include the proof of the theorem in my talk because it is not hard and very, very beautiful and instructive, but well, I decided against it because, well, I already have 2 proofs. But well, if it were a live talk, we could have discussed it, but talk like this online, probably no. Anyway, it's a very, very beautiful argument, simple and instructive and really aesthetically nice. And now we are ready to start discussing Dimitrov's work. So we will prove the following. Theorem. So alpha, algebraic integer of degree d, non-zero, not root of unity, p, a prime number. Then the logarithm of the house of alpha is bounded from below by this quantity. So constant log 2 over p squared and 1 over d. And here, well, you remember that in Dobrowolski argument, we needed to take big prime p. Here, it will work for any p. In particular, we can just take p equal to 2. And this is what Dimitrov does. He argues in his article with p equal to 2. But I think it will be probably more kind of conceptual to work with arbitrary p here. And well, if we take p over 2, we obtain exactly the claimed result of the constant log 2 of. here, well, log 2 comes from the transfinite diameter, and p squared comes from the Schoenemann congruence mod p squared. Yeah. So let me make, well, some reminders. So alpha 1, alpha d are the conjugates of our alpha. F of t, let's call it minimal polynomial. And fn of t is again a polynomial whose roots are just nth powers of the roots of f. And I remind you, well, this Schoenemann congruence. And well, like Dobrowolski used it with k equal to 1, but Dimitrov is using it with k equal to 2. So fp is congruent to fp squared mod p squared. Now, let us, well, some very simple lemma, which in particular explains what I said, that in Dobrowolski's argument, we can easily find suitable p. Is the following, that if we have just algebraic number, not necessarily integer, simply not a root of unity, then first thing, the fields q of alpha and q of alpha p, either they coincide or their degree is p of this over this. So it's kind of beginning of what's called Cummins theory. Well, it's a bit delicate argument, but very classical. And second, if alpha to the m and alpha to the n cannot be conjugate, well, unless m and n are the same or plus minus the same. So, well, if they're conjugate, then alpha must be a root of unity. So it's well, easy exercise, and well, using this lemma, we show that we may assume that the roots of fp, which are alpha 1 p alpha dp, are all distinct. Why? Because if they are not all distinct, then this means that the field q of alpha p is not the same as q of alpha. So this means that it's that alpha to the p is of degree d over p, and so we can use induction. And by induction is the degree. And by induction, we simply obtain this lower bound for the house of alpha to the p, which gives, of course, the lower bound, the wanted lower bound for the house of alpha. So from now on, we will assume that all these numbers are distinct. And the second part of the lemma implies that, of course, fp and fp squared have no common roots. So otherwise, they will simply be alpha and alpha p squared will be conjugate, and we see that it's not possible by the lemma. And well, good. Now we consider the rational function. We divide fp by fp squared. It's a regular function and non-vanishing on the simply connected domain with C with H removed, where by H we take the hedgehog whose vertices are exactly the roots of both these polynomials. So p powers of the roots of the conjugates of alpha and p squared powers of their roots. So it's hedgehog with 2D vertices. And since it is regular and non-vanishing, we can take the pth root of this function. We normalize it to have value 1 at infinity. And then again, it is a regular function. And know that it cannot be rational. It cannot be a rational function because look, the roots in the numerator are all simple, and they're distinct from the roots of denominator, just by our assumption in the previous slide. Yeah. And so when we take the pth root, we cannot obtain just a rational function here. And we will see in the subsequent slides, and this is where we are going to use Schoenemann's congruence, that this function, this pth root, has a Taylor expansion at infinity with integral coefficients. And as long as we have this, we're done, because on the one hand, Polya gives us lower bound for the transfinite diameter, at least one, cannot be smaller than one, because the function is not rational. On the other hand, Dubinin gives the upper bound. And we compare the lower bound and the upper bound, and we obtain what we want. So we're only left with proving that the coefficients are integral, and this is very, again, very beautiful. You see, the proof of Dimitrov is so simple that I was really amused when I saw it, because it does not use any new mathematics, only very classical things, and very simple, but so far nobody managed to do it. Now let us see why the Taylor expansion at infinity has integral coefficients. And the idea is that when we have pth root of this guy 1 plus p squared t, then we obtain a series with integral coefficients. This is why, because for this binomial coefficient, IP choose k, 1 over p, sorry, choose k, the periodic order is k, because it's 1 over p, and k factorial, and plus the periodic order of k factorial, because of k factorial in the denominator. And this is strictly less than 2k. And we know that p is the only guy that emerges in the denominator. All other primes are not in the denominator of this guy. So which means that when we multiply by p to 2k, we obtain an integer. And well, note that just p to k is not enough. So this is not a series of integral coefficients. And well, in our case, we are lucky we have this congruence mod p squared. And so we write fp as fp squared plus p squared times some other integral polynomial, and which is of degree at most d minus 1, because fp and fp squared have the same leading coefficient 1. So degree is at most d minus 1, and our u is given by this formula. And now it becomes basically clear that it must have integral coefficients at the expansion, but well, still I will give the proof. So let us write them. Well, let b be the coefficients of fp squared, let c's be the coefficients of g. And well, what's the power expansion at infinity? We should multiply the denominator and numerator by z2 minus d. And this is what we obtain. So we obtain 1 plus p squared z2 minus 1 and times some v, and the pth root of all this guy, where v is a certain rational function, and clearly this rational function has at infinity integral coefficients. And then our u, also our pth root, also has integral coefficients, because we just substitute something with integral coefficients here, and here also integers, so everything is integral, so we have integral coefficients. And this concludes the proof of the theorem of Dimitrov. So I personally find it totally